In this video, we're going to look at some examples of writing nuclear equations for fission reactions. So remember that nuclear fission is when I have a large nucleus and it splits roughly in half into two smaller nuclei. This gives off a tremendous amount of energy, and it also gives off neutrons. Now these neutrons are important to sustain a nuclear fission reaction because then they can go on to induce fission in other fissionable nuclei. Now that idea is important, and there are two types of nuclear fission. The process that's shown here is called neutron-induced fission. And that occurs when I have a nucleus that absorbs a neutron, making it particularly unstable, and then giving rise to nuclear fission. There is another type of fission that's somewhat less common called spontaneous fission. In that case, we don't have this neutron here, and we just have a nucleus all by itself that spontaneously decides it's going to split off into two smaller halves and then also give off some neutrons. So in this first example, we want to write the nuclear equation for the spontaneous fission of uranium-235 to produce tellurium-137 and zirconium-95. So we can immediately start writing down parts of the problem. So they've given me the mass numbers of the parent and the two daughters, and so I can immediately say, okay, I know that it's uranium-235 that we're talking about. It's spontaneous fission, so there's only going to be one reactant. There's going to be no neutrons on the left-hand side. And then this is going to make tellurium-137 and zirconium-95. And we know that this is also going to produce some neutrons, but we don't know how many yet. But that's something that we'll be able to figure out. So we're going to make some number of neutrons. All right, now what I'm going to do next is go to the periodic table and get the atomic numbers for uranium and tellurium and zirconium. All right, so I've got uranium down here. It's atomic number 92. I've got tellurium right here. It's atomic number 52. And I have zirconium right here, which is atomic number 40. So I'm going to go ahead and put those into my nuclear equation. Okay, so we said that uranium was 92. We said that tellurium was 52. And we said that zirconium was 40. Now one thing you'll notice right away, the atomic numbers of the two daughters add up to the atomic number of the parent. And that has to be the case because the only other thing we have are neutrons, and of course they don't contribute to the atomic number. So 52 plus 40 is 92, is 92. So to figure out the number of neutrons, we're going to use the mass numbers, right? Because the mass numbers of the neutrons is not zero. But we'll do this just in the same way that we've balanced other nuclear equations. The mass number of all the things on the left, in this case just the uranium, has to be equal to the sum of the mass numbers on the right. So on the reactants, I've got 235. On the products, I've got 137 plus 95 from the zirconium plus some number of neutrons. Right? I don't know how many I have, but however many I have, it's going to be x, which is this number, times 1. So by solving for x, that's going to tell me how many neutrons I have. So 235 is going to be 232 plus x. So I've got a mass number of 235 on the left, 232 without the neutrons, so I think we can see we're going to need, I'll subtract 232 from both sides, x is going to be 3. So I need 3 neutrons to balance this. And so this is our equation for the spontaneous fission of uranium-235 to make tellurium-137 and zirconium-95. All right, so I've got one more example where we'll do a neutron-induced fission example. Okay, so now they want to do the same thing, but now our reaction is going to be the neutron-induced fission of plutonium-239, and again they give us the two daughter products. So now in this case, I can write down part of the problem. So I know that's uranium-239. Now because it's a neutron induced, that means that there's going to be a neutron on the reactant side. And then that'll make my products. That'll make the gold 204. That'll make the phosphorus 31. And then again, I'm going to make some number of neutrons. All right, so let's again go to the periodic table and get the atomic numbers for these pieces. So plutonium is 94, gold is 79, and phosphorus is 15. So I can put that in on the next slide. All right, so we said that plutonium is 94, gold 79, and phosphorus 15. And again, we see that 15 plus 79 is 94, because the neutrons, of course, don't contribute to the atomic number. So I'll use the mass numbers to figure out the number of neutrons on the right-hand side. So on the reactant side, I've got the plutonium, always one neutron with the neutron-induced fission. That has to be equal to the gold, the phosphorus, and then however many neutrons it's going to produce. So on the left, I've got 240. On the right, I've got 235 plus, of course, x times 1 is just x. And so we can see that x is going to be 5. So this is going to produce 5 neutrons. And so that's our equation for the neutron-induced fission of plutonium-239. The difference between neutron-induced and spontaneous and neutron-induced, I'll always have the one neutron on the reactant side. In the spontaneous, I only have the parent.